Good afternoon, thanks for coming. My name's Ruth Keogh. I'm also at the London School in the Department of Medical Statistics. And I should confess that I don't really know anything about biofortification of foods, but I'm going to talk to you about some statistical issues related to dietary intake as a response variable in intervention trials. So I hope that people will be able to see how some of the studies that they're doing involving fortified foods could relate to this work. And what I'm going to talk about is based on this paper published a couple of years ago in Statistics in Medicine with the same title. This work was led by Lawrence Friedman and also with Ray Carroll, Janet Tooze and Sharon Kirkpatrick. So this is what I'm going to talk about. I'm going to give a little bit of general background to the problem of measurement error, because I guess that's the big problem here, that it's very difficult to measure what people eat. And then I'm going to put a focus on dietary intervention studies in which we've obtained biomarkers and also some self-reported information on what people have eaten. And I'll then go on to talk about error in dietary measurements, how we can make use of these different kinds of measures that we may have of people's dietary intake. And I'm going to use an example which is from a trial of nonpharmacologic intervention in the elderly. So let me start with just some general points about measurement error. And Ray Carroll, in his nice book on measurement error, describes at the beginning of the book the triple whammy of measurement error. So he says the impact of error in measurements, here thinking about measuring dietary intake, are bias in parameter estimation, so in this case our intervention effect, loss of power for detecting signals and masking the features of the data. And so there's a huge literature on dealing with measurement error and the impact of error. Most of it, or a majority of it, is focused on error in explanatory variables. So I'll say a bit about that first before moving on to error in outcomes. So this picture just depicts the setup that we have. So let's suppose we've got some true exposure. I've said exposure here because I guess I'm used to the setting of observational studies, but it could be some kind of intervention. And we're interested in how it relates to some outcome. But instead of observing the truth x, we observe an error-prone version of it. So what we observe is x plus error. And we can see what the impact of this is just by imagining we're doing a simple linear regression of y on x. So here's the true relationship. And as we add error into x, you can see that the relationship becomes attenuated. And there's a lot more scatter as well, so we lose power to even detect a relationship. So moving on to error in outcomes. So now, let's suppose we're interested in some outcome y, and in this setting I'm imagining this being a measure of dietary intake. But instead of observing the true intake, we observe some error-prone version of it. And let's suppose that we're really lucky and we only have random error. Now, interestingly, the effect of random error in an outcome, it actually doesn't give us any bias. It gives us a loss of power, but it doesn't bias the association. But that's only for random error. I think what we face in studies of diet, so where y is a measure of dietary intake, is that we don't have random error. We probably have systematic error and also differential error, where the error is affected by what we're interested in, our intervention. So this is a setup I'm going to focus on, a randomised trial where we've got some randomised intervention, an outcome which is dietary intake. So it may be that investigators are studying how to get individuals to eat a healthier diet, let's say, and the focus is on achieving some kind of dietary change. And I'll just mention this example, which comes from this trial in the elderly, published a few years ago now. And I'm going to focus on two intervention groups. Some people received or were instructed to follow a sodium lowering diet. and other people didn't. There was actually a weight loss arm as well, but I'm going to ignore that here. And there were a number of outcomes in this trial. The one we're going to focus on is sodium intake. So the intervention effect that we're interested in here is that the mean difference in sodium intake at the end of the trial between these two intervention groups. And I realise this is different from the kinds of examples that are faced in low and middle income countries, where perhaps you are typically trying to get people to eat more of something. Here we're trying to get people to eat less of something. So in this study, they had two measures of dietary intake. They had some self-reported measures, which was via a 24-hour recall. So they asked people what they ate yesterday. And studies show that people are not very good at remembering what they ate yesterday. And they also had some biomarkers. So they had two measures from each individual of urinary sodium. And we assumed in the example I'll give later that 86% of dietary sodium is excreted in the urine. So how good are these measures of the dietary outcome? Well, self-reports, the very nice thing about them is that they are cheaply measured. But the problems with them is that they are likely subject to non-random errors, and they may be influenced by which intervention was received, especially if people are trying to demonstrate to the investigator that they were compliant with their intervention. Because people in my example study, they knew that they were supposed to be following a sodium lowering diet. Biomarkers have some nice features. They're objective, measured without knowledge of the intervention group. We hope they're subject only to random error, but they have this big drawback of being expensive. And like Edward mentioned, there often is no biomarker available for the nutrient that we're interested in. So I'm going to focus on this kind of setup where we have a study in which we've obtained self-reports on everybody in our two intervention groups, because that was something which was relatively cheap to do, and we've obtained biomarkers in a sub-study. And maybe I should just mention that a paper came out in the Journal of the American Medical Association very recently, maybe just a couple of weeks ago. I became aware of it, which was quite highly critical of a lot of research in nutritional epidemiology. I didn't agree with everything in that paper, but one of the recommendations was that we need more experimental studies looking at diet. So I guess this is relevant for that as well. So I'm now going to take you through some statistical models for the error in these measurements that we have. And let's suppose that what we're really interested in is a person's true dietary intake, but not really ever observe this, but it's there in the background. So that's T, and I've got these subscripts here where I is denoting my intervention group and J is representing the individual. I've just written it in this form so that my intervention effect is the difference in mean true intake in the two intervention groups. Instead of observing this truth T, we observe these self-reports. I'll call those Q. And these, we think, are probably subject to some systematic error. So they have this relationship with the truth. We also are concerned in this situation that not only is the error systematic, but it's differential. So the magnitude of the bias is different in our intervention and control groups. And so that's when these alpha parameters are different in the two intervention groups, or in the setting of non-differential error, these alphas are the same in the two intervention groups. So that's a model for the self-report. The biomarkers, we hope, are subject only to random error. So we could write the biomarker, I'll call that M, as the truth plus some purely random error. And this means that we can obtain an unbiased estimate of the intervention effect in a straightforward way using the biomarkers. It's the difference in the mean measurements in the two groups. But the problem being that we may only have those measures for a relatively small number of individuals. So how can we obtain an estimate of the intervention effect in the self-reports? Well, if we just take the difference in the mean of the self-reports, that's going to be biased because of this systematic error. If we can estimate the form of the systematic error, then we can obtain a corrected estimate of the intervention effect using the self-reports. But to know the form of the systematic error, we need to estimate these alpha parameters. And to do that, we need some repeated biomarker measurements. We don't have to have those for everybody, but we need to get a handle on what the form of the error is. And in order to do that, we need some unbiased measurements on at least a subset of our study sample. And so the questions that we were interested in this piece of work were what methods could be used to take advantage of this combined data that we may have, or should we just focus on the biomarkers? In what circumstances are these biased self-report data helpful to us in addition to this unbiased data? So we used this weighted combination, or we considered a weighted estimator of the intervention effect, which is a weighted combination of the estimate we could obtain from the biomarkers and the unbiased estimate we could obtain from the self-reports. It takes this simple weighted form, and this was described by Bonacorsi some time ago. So this was the estimator we were focused on as our combined estimator. So what we were particularly interested in is what's the contribution of the self-reports to this combined estimate. And I'll just try and give a little idea of this. And the answer is it depends on what type of error we have in our self-reports. If we've got differential error, so if we've got different level of systematic error in our two intervention groups, then it turns out that our estimate from the self-reports is really no different from the difference in the biomarkers, because it involves a term which tends to 0. And so that suggests that if we have differential error, we're not going to gain much by using all our self-report data in addition to our biomarker data. So we may have wasted our money in collecting these self-report information. If the error is non-differential, so if we could still have systematic error, but if it's no different in the two intervention groups, then there's a suggestion that, based on theory, that the combined estimate could be more precise than the estimate based only on biomarkers, so that we could do better by making use of all this data rather than just the green bit. So we looked at some simulation studies in order to make some comparisons. So we looked at the estimates that we might get by using the biomarkers only in that small subset of people, and we looked at what we would get from our combined estimate, so to see whether in practice it's useful to make use of this self-reported data. And the things we were thinking about in making these comparisons, well, it depends on the form of the error in the self-reported data. So we considered the reliability of the self-reports relative to the biomarker. And reliability is about the repeatability or the correlation between repeated measures. And we also considered whether we have differential or non-differential error in the self-reports. So I'm not going to give you too much detail about what we put into the simulation study, but we based it on the trial in the elderly study. We considered different reliabilities for the self-reports relative to the biomarker. Studies where we have different proportions of individuals who had the biomarker available and the differential and non-differential error. And what I'm going to show you in the results is a measure of efficiency. So the efficiency of using the combined estimator versus only using the biomarkers. So what do we gain by using all our data versus only using a subset of our data? So these are some of the results. When we have differential error in our self-reports, so this graph here is showing us, along the bottom we've got different settings for the reliability of the self-report. So where we've got good reliability, moderate or low. So low reliability is when the repeated self-reported measures are not highly correlated with each other. And going up the side here, we've got the gain that we get in efficiency from using all the data versus just using the biomarkers. So we see here that, and this is in the red, is when we've got biomarkers in only 10% of our study. So we see that if the reliability of the self-reports is good, we can gain quite a lot in efficiency by using them. But when it's not so good, or rather poor, we gain very little by using that data. And the more people that we have biomarkers on in our study, the less we gain from also making use of the self-reports, which is intuitive, of course. This is where we had differential error, and we expected from the theory that we wouldn't gain much, and that was in very large samples, and this is in a finite sample. So we see that if we've got reliable self-report data, we can still gain something in this setting. We gain more, as we expect from the theory, in the setting of non-differential error. So this again is the gain in efficiency from using the self-reports versus only using the biomarkers. So we see that even if we've got biomarkers in half of the people in our study, we can still gain quite a lot in efficiency by also using the self-report data. And I just want to finish off by giving an example of what this could imply for study design. So this is an example where our reliability, if we imagine a setting where the reliability of our self-reports is similar to that of the biomarkers. So the efficiency of a study in which we had 100 people with both self-report and the biomarker and 900 people with the self-report only would be similar to or equal to that of a study with 157 people with biomarkers only. We've got some other examples here. If we've got a study of 1,000 people, a quarter have both the measures, 3/4 have the self-report only. This is equivalent to, in terms of efficiency, to a study where we've got biomarkers on 372 individuals, and some other examples here. And so when people are doing studies, they really need to weigh up how much these things cost relative to each other. It may be very cheap to obtain information on 900. I suspect these sample sizes are quite unrealistic compared to the kinds of studies that you're doing. I'd be interested to hear about that. But you have to think about how much does it cost to obtain data on 157 people using biomarkers versus 100 people using biomarkers plus 900 people with a self-report. And that's up to the investigator and the setting that they're in. I'll just finish off with some results from this study. So there were about 300 odd people in each of the intervention group, and then we measured their sodium intake at the end of the study. The reliability of the self-reports here was very low. So this is a correlation between repeated self-reports of a quarter. There was also evidence of differential error in the two treatment arms. The reliability of the biomarkers was much better. So these are estimates of the treatment effect. Using the self-reports only, we think that's biased because of systematic error. Using the biomarkers only in 10% of individuals, this is our treatment effect, so suggesting that people in the intervention group did have lower salt intake. And this is what we gained from also using the extra self-report data on the other 90% of individuals. We gain, the treatment effect estimate is almost the same, and we gain almost nothing in terms of efficiency. So just some summary points. Self-reported outcomes are subject to error, often differential error. That's going to give us biased intervention effect estimates. I think if there is one, it's a good idea to incorporate biomarkers into your study design, ideally repeated biomarkers. But I think there's still some role for self-reports alongside biomarkers in some circumstances, and you have to weigh up what your circumstances are. And I think it's something which is not very well appreciated, I think, is that the impact of measurement error should be considered in sample size calculations. Something that's lacking is a tool which helps investigators to plan their trials, I think, which takes into account things like these measurement error issues, but also the relative reliability and the relative cost of these different measures which they may be using. And as Edward also mentioned, the situations in which an unbiased biomarker of intake is available are currently very limited, which hampers all of this. So thank you.